see spread throughout the universe here. The box represents the space of the universe. So as I press play, gravity will start to play a role and start to create the universe as we know it of today. So as you see, gravity's playing its role right now, and it's pulling the hydrogen into filaments and creating something that astronomers know as a cosmic web. And this is something this is how the large-scale structure of the universe looks today. It looks something like this. As you see, there's various different nodes here in the picture, and these are where the galaxy clusters are, a lot of star clusters are, and where all these things are formed. So as you see, this is the overall picture of what the large-scale structure looks like if we were able to just zoom out and look at the universe as a whole. Back to my presentation now. And so, what astronomers like to ask is where does the large-scale structure come from? How are we able to see this structure? And so a quick little explanation is after the Big Bang, gravity took over and formed the large-scale structure by pulling the hydrogen into filaments and clusters, as we see in the simulation that I just showed you guys. And so here's a picture. It's a 3D picture of space, the space and time of the universe. So right here represents time. This being the beginning of time, and this being the present time, like right here where we are at right now. There's also dimensions of space in here, which in this direction will be represented, the x direction of space, and y direction of space will be represented here. The third dimension is the z direction, which is suppressed because you can't show a four-dimensional picture on a 2D picture. And so we want to know how are we able to observe this? How are we able to get this large-scale structure? And we can do that by using quasars. Now quasars have two main components that makes it really unique. The first component is a supermassive black hole, which can be up to 1 million or up to 1 million times bigger than our sun, or even bigger than that. Also, something that you guys may know about black holes, or what you guys may think you already know, is that black holes suck in or pull. What astronomical terms that's called is called accreting. And so this disk here, right here, will be the accretion disk, where all the matter that will soon pass through the event horizon of the black hole will go through. What's unique about this accretion disk is that the matter that's within the accretion disk is rotating near the speeds of light. At this time, the matter is also creating a lot of friction. It's heating up very, very hot. All the materials in there are ionized. And so what it's going to at those speeds and going up to those speeds and that hot, it makes the quasar very, very bright. And just to kind of show you guys on how bright these things can be, I would like to point to this image right here. This is a Hubble telescope image, and it has various different space objects in here. The first object I'd like to point out is here. This is a star that's within our Milky Way galaxy. It's about 1,000 light years away. It's fairly bright in the picture. Here goes a various amount of galaxies containing about 100 billion to 1 trillion stars. And they're still fairly bright as well, and they're about a few 100 million light years away. This little circle thing there is a galaxy that's 7 billion light years away. And you can still be able to see it. Now the most significant object is right there in the center. And that is a quasar. That is 9 billion light years away. Now wait, that's a quasar, that's 9 billion light years away. Very, very, very far, but as you see, it is as bright as an object that's in our own Milky Way galaxy. And so as I said before, quasars can be very, very bright, and that's even brighter than something that's in our own galaxy. That should be mind-blowing. Let's be wow. For sure. And so let's take that same quasar that was 9 billion light years away, or 9 billion light years away. And so on a space-time diagram, what that means is that it's 9 billion years in the past. So it will be here on the space-time diagram. The present will be represented here. This is a Milky Way galaxy where we are at right now. And so as the light from the quasar leaves, it travels through space and time. And so this yellow line represents the light leaving and traveling through space-time. And so as it's traveling through space-time, it's going through various objects in there and throughout the universe. And these objects are hydrogen clouds, one of the most abundant objects within the universe. While also going through hydrogen clouds, also pass through dark matter as well. And what some of you guys may know about light, as it passes through different elements and objects, it creates a spectrum. And so, therefore, the light of quasars carry information. And so, for this, I can show that by this picture here. So this is a quasar. This is quasar light when it first leaves it. It does not pass through anything. It has a full spectrum. And now as it goes throughout the universe, it's passing through hydrogen and other elements, which creates absorption lines within the spectrum. And so when it gets to us, or whatever satellite or Hubble telescope or whatever measuring tool that we're using, we get a spectrum that looks like this. That once was once a full spectrum, is now something with lines in it that tells us information about what's in between the quasar and us. It tells us stuff about hydrogen, or hydrogen in the universe, or the other structures that's within the universe as well. To kind of show you guys what my project was about and what I specifically did, I wanted to point to this diagram here. To the left, there is those yellow dots represent quasars. There are also the blue blobs in the picture are hydrogen clouds, and our planet Earth here. And so, as I said before, as the light travels throughout the universe, it carries information and it creates a certain specific kind of spectrum. And so, what I wanted to do was find a correlation between two quasar pairs, meaning like what is the correlation between two quasars at a certain distance, and how likely will they be correlated? And so, I would like to point to these two quasars here. So, these two quasars are passing through a similar cloud, which means that their spectrum will also be similar because they pass through the same object. And so I would say that these two objects here will be correlated versus this quasar and this quasar here. They do not pass through the same clouds. So therefore their spectrum will look alike, and therefore they won't be correlated, highly correlated. How I measured the correlation was if something was close to 0, it was not correlated, and if something was closer to 1, it was highly correlated. And so some of my results that I got was from this graph here. And the x direction is angular separation, which is in arc minutes. For those who don't know what an arc minute is, imagine if you have a penny and you have a drill and you drill out Abraham Lincoln's eye and you hold that at arm's length and you look out through the hole. That would be 1 arc minute in the sky. And so it's a very fine point in the sky, very, very fine point. And so I did my research under 2 arc minutes. And under 2 arc minutes, I was able to get 1,500 quasar pairs. But so what my data is telling me here is that under 2 arc minutes, most quasars are highly correlated. Now, just to let you guys know, these are preliminary results. Me and my professors are still working on if this is true or not. But what that would mean if they're all correlated under 2 arc minutes, that what I'm able to obtain for that is that the cloud that they're passing through must be at least spread within 2 arc minutes. And so that must mean that the hydrogen cloud that's passing, that all the quasars that pass through is very, very large. Therefore, all the quasars can pass through it and have a similar spectrum. And so what I look to do in the future is spread this within 10 arc minutes and see if we get a similar trend, or see if we spread the sky separation, should the correlation decrease, which should be suspected, as I showed you guys in the diagram previously. And also other research papers that I read as well, that was a similar trend. And so I'm working on that now, and hopefully I'll be able to obtain that information. But thank you. That was all for my research. But I'd also like to give some acknowledgments. First of all, to all of you guys who come here to support me and come here to watch me speak. To my beautiful family who's right there, being very supportive throughout the trip. Pacific Fund for funding me to be able to go to Trieste, Italy to do this research that I did. Also the physics department, they helped support me as well, help me get this trip. And most importantly, Professor Hedrick and Professor Flowick, who are here in the audience. Without them, I would not be able to have this great experience and be in front of you guys here today to be able to speak. So grazie mille, bellissimo ragazzi. What that means in Italian is thank you very much, beautiful people. And any questions? if you guys don't have any questions, there's some questions there that I'll be happy to answer. Yes.
So on the diagram, we had the correlation as a function of arc minutes. I noticed there was some where you're near 0 arc minute separation, you still have them as not 100% correlated. And
so right here.
Yeah.
Yeah.
So, I mean, if they're not even separated, don't they have to be passing through the same cloud?
Oh, sorry, say that, repeat that again, sorry.
So if they're not even separated by an angle in the sky, they're right on top of each other in the sky, how is it that they're not passing through the same cloud?
Okay, so there's some things that I did not tell you about this data. So some things about this, so this is a large data set. I work with Sloan Digital Sky Survey, one of the biggest surveys for quasars. And so since there's such a big survey, their data is probably not always very, very good. And so their signal to noise ratio for some of the data was very, very bad. So of course in all data, there are gonna be some outliers and there are gonna be some falses in here, but I'm not really focusing on this one point, but where the majority are. So that may be due to the error that the signal to noise ratio of that spectra was very, very low, like really, really low. So thank you for that, I appreciate that.
What about the distance of the quasar from Earth, where you make the observation, is vastly different, right? So wouldn't it be logical that you see differences if the quasar is closer to the Earth? Its light has traveled through less hydrogen. It's on the same path than the quasar that's a couple of billion light years further away.
That could be true. But like so ask that question. I'm sorry, I don't think I fully understand.
Well, you measure light, right? Yes. The absorption spectrum, but essentially what happened to the light, the emitted light from the quasar on its trip from the quasar to the Earth. So it travels a huge distance and it encounters a lot of matter along the way. So even though the two quasars, follow up on Dr. Dutoy's question, even though they're not separated by their
by that much, they pass.
They're separated by the distance.
So
the one that is further away, shouldn't it be expected to have a slightly different absorption?
Most definitely. I wish I had some pictures of some spectrums that were redshifted at different distances that I could show you. So that is true, but the overall structure of the spectrum, because certain quasars have an overall structure that's pretty similar throughout, should still be the same. And there's a unique part of the spectrum. Are you a chemist, biology? So you know about like Lyman alpha transitions and stuff. So they're called Lyman alpha 4s, part of the spectrum. And so what we're looking at is that spectrum. So yes, even though they're redshifted, there should be some similarities within the spectrum. Like so, if the quasar, what I would be comparing them, I wouldn't be comparing the light that's traveling before the quasars meet. I'll be comparing them at the same. They should be like at the same distance. So all the light that traveled before, I cut that out of the spectrum.
Oh, I see.
You kind of get what I'm saying. So only look at the part of the spectrum where they're at the same distances.
I see.
You know what I'm saying?
I see. So normalize it.
Yeah, so normalize it and make sure that that we won't make that in play.
Can you kind of talk about your experience in Italy and how that helped you, with your project and what you're working on?
That was one of the questions. Is there anything specific that you'd like to talk about?
Like how it helped, like did it benefit you in any of your project that you're currently working on, like other than being out of the country? Like did you, anything that was enriching to your work?
Okay, so there's a lot of enrichment, but the enrichment didn't come till after the struggle. So because first of all, I would like to say that this was my first time out of the country. So I was out there by myself. It wasn't like with a program or anything like that. It was just Professor Floyd had a connection in Italy and said, "Oh, go out there in Italy and go do research." In the beginning, I would say going out there made it harder for me because first of all, I have no friends. I didn't have anyone to talk to. I didn't understand the language. I was like, I wasn't comfortable at the place I was at because this is my first time there. So at first it played at a disadvantage. But being in a foreign country where you don't speak the language, you don't do all that, it gives you a lot of time to focus more on this rather than having fun with friends and stuff like that. And so I spent a lot of time thinking about my research, spending a lot of time thinking about like what could I do to, because all this was done through coding. And so it gave me a lot of time to think about how can I make my code more efficient, or how can I make my program do, how do I make my program subtract the distance of light before, so think of all those things. It really didn't, so for the biggest thing it helped me with was how to think, first of all. It taught me how to think because I was isolated. I was in a place that I'd never been before, and I was alone. It also working with my advisor helped me a lot as well. And then, so, this is my advisor here. She looks happy and stuff in this picture, but most of the time she had a serious face. She's a very serious person, and she believes in the method of sink or swim. Really, when I mean sink until you're almost about to die, and then you back up. And what I mean by that, the only amount of information I got about the project was within the first day, and that was about like 2 hours. So you got to remember, I'm jet lagged. I traveled 19 hours across the world, and so she gave me information about the project, and that's the only time I talked to her. Throughout the rest of the project, I'm on my own, and so that helped me learn how to think on my own and how to work on my own in a way. But I definitely did die a lot during the time. But thanks for asking that. Yeah. Any other questions? Is my project about Interstellar? Oh, yes, yeah. Gargantuan, no, I'm just kidding. It's not. Have nothing to do with it. Well, if there's nothing else, thank you guys for coming, and I appreciate it. If you guys want to ask any other questions over here, I'll be here to talk. But thank you guys.